So given any particular LDPC code, we have an algorithm that we can implement. We had a message passing rule, or the belief propagation algorithm, which works by initializing messages and then iteratively updating the messages along. Now the question is, well, for a given channel, let us say the binary erasure channel, not all codes are going to work the same way. Some of them are going to have low probability of error if we implement this particular algorithm. Some codes will have a high probability of error if we implement this particular. So then how do we construct a good code? How do we construct LDPC codes, and how do we analyze them? So it turns out that it's very, very difficult to analyze a single LDPC code. So instead what we do is we study an ensemble of LDPC. So for example, the class of all DV-DC regular LDPC. So this collection of codes is easier to analyze because you can say something about an average code picked from this. It's very difficult to analyze the performance of a single LDPC code, but on average, you can use certain techniques from probability to characterize the performance. Right? That will mean that most codes, in fact, we will show that most codes from the class of, let us say, DV-DC regular LDPC codes achieve a certain error probability over the BEC or the BSC. So one class of, or one ensemble of codes that we saw was the class of DV-DC regular LDPC. And for that, we studied what is called the configuration model. Essentially, you put in DV sockets for each variable node, DC sockets for each step node, construct a random permutation, and then so that will basically give you one particular LDPC. Gives a random LDPC. Now the question is, suppose I wanted to construct an irregular LDPC, by which I mean that I don't want every left vertex or every variable node to have the same degree. Maybe I want half of the variable nodes to have degree 3 and maybe half of the variable nodes to have degree 4. One way of constructing one class of LDPC. It turns out that such classes wherein you have this slight irregularity, these actually can achieve capacity. Whereas the class of regular LDPC codes, they don't get you all the way up to capacity. Okay. So in particular, we are interested in this class of irregular. Wherein, so we have a total of n variable nodes and m check nodes. Okay. And among the n variable nodes, let us say that n by 2 variable nodes will have degree 4, and n by 2 of the variable nodes will have degree 5. And maybe out of the m check nodes, maybe m by 2 check nodes will have variable 10, and m by 2 of them will have degree 2. But how do we actually formalize this? So it turns out that one way of sort of representing an irregular LDPC code is using the so-called degree distribution. This is basically another way of saying exactly the same thing, that these many variable nodes will have degree this, and these many variable nodes will have degree this, and so on. So we represent this using a polynomial, the degree distribution polynomial. We'll call lambda of x. So this is going to be going from max I x raised to I, where this is sort of a coefficient and this is whatever x raised to the I. So the way you should think about this is that lambda I is the number of variable nodes having degree I. Okay, and similarly, we can define the degree distribution for the check nodes, which is they're called P of x. So this is going to be a polynomial, I going from 1 to Pi x raised to I, where Pi is basically the number of check nodes having degree I. Okay, so let's do a quick example. Suppose I have the following LDPC. So this is one particular LDPC code. Can you tell me what is lambda of x equal to? So remember, this is the degree distribution for the variable nodes. Right? So this is going to be some polynomial. What is the maximum degree on the left hand side? Is there any vertex on the left having degree 3? Oh, okay. So really, I mean, yeah, even otherwise, it's just so this one has degree 2, degree 1, degree 1, degree 2, and degree 2. So the maximum degree is 2. The minimum degree is 1. Okay, so now how many vertices have degree 1? So this one, and this one. So there are 3 variable nodes with degree 1. So it's going to be 3x plus, how many nodes do I have degree 2? About P of x. This is for the check nodes. To x square plus x cube. One check node with degree 3. Okay. Okay, that's good. So now let's try to make some observations regarding lambda of x and p. Suppose I try to evaluate lambda of x at x equal to 1. So what is lambda of 1? Okay, that's 5. What does that correspond to in this case? So when I evaluate, say, this polynomial lambda of x at x equal to 1, what do I get in general? So if I take any polynomial, say a0 plus a1x plus a2x square plus a2x cube and so on, if I evaluate this at x equal to 1, what do I get? In terms of the coefficients. So what will it be equal to? What will f of x be equal to? Correct. But I'm telling you that it is a0 plus a1x plus a2x square plus, let's say, 3x cube. So what will f of x at x equal to 1 be equal to? Correct. It's going to be the sum of all the coefficients. Right? So it's going to be the sum of the coefficients of this particular polynomial. But what is that actually going to be equal to? Okay, so I have this polynomial taking the sum of the coefficients. But what does each coefficient represent? It represents, so lambda I is the number of variable nodes having degree I. So if I sum over all possible I, what do I get? Correct. Not outgoing, but so this is the number of variable nodes having degree I. Right? So number of variable nodes having degree 1 plus number of variable nodes having degree 2 plus number of nodes having degree 3 and so on. But when you sum all of them, what do you get? Exactly. So number of variable nodes. Right? So lambda of 1 is always going to be equal to n, right? Which is the number of variable nodes. Similarly, what is p of 1 going to be equal to? It's going to be the number of checks. Always going to be. Right? Now, if I take, so I have this, right? Let's try to evaluate something else. So let me take the derivative of lambda of x. Okay. So I will get lambda 1 plus 2 lambda 2 x power 1 plus 3 lambda 3 x square. So this is just summation I equal to 1 to L max I lambda I x raised to I minus. Right? Now if I evaluate this lambda prime at x equal to 1, what do I get? Correct. So it's lambda 1 plus 2 lambda 2 plus 3 lambda 3 and so on. Is equal to something. So let us take this particular example. Okay. Can you compute lambda prime of 1? It's going to be 3 plus 4. So 3 plus 4x. So evaluate at 1. So I get 3 plus 4 equal to 7. Okay. What is the number of edges in this particular graph? Okay, so now let me take p of x, take p prime of x, evaluate it at x equal to 1. What do you get? Seven. Okay, isn't that a bit surprising? Is it going to be true for all graphs? So take this particular example that we have, smaller one. What is lambda of x in that particular case? 2x plus 2x plus 2x squared. So now we can compute lambda prime of 1. Okay, what is the number of edges? What is p of x? What is p of x? Going to x cubed. 2x cubed, and then lambda prime, sorry, p prime of 1 is going to be 6. Number of edges is also 6. Okay, something funny going on here. Will it always be equal to the number of edges? So let's try to think about this. So we know that lambda prime of x, lambda 1 plus 2 lambda 2 x power 1 plus 3 lambda 3 x square and so on. Right? So now let us look at lambda 1. So lambda prime of 1 is going to be lambda 1 plus 2 lambda 2 plus 3 lambda 3 and so on. Now let's count the number of edges. Okay. So how do you count the number of edges? So what will the number of edges be equal to? It is going to be equal to the sum of the degrees of all variable nodes. You agree? So now, how many variable nodes have degree 1? Lambda 1. Right? How many nodes have degree 2? How many nodes have degree 2? Lambda 2. Correct? So if you take the sum of the degrees of those, it's going to be 2 times lambda 2. How many nodes have degree 3? Lambda 3 nodes. And what is the total number of edges incident on them? What is the contribution to the total number of edges? It is 3 into lambda 3 and so on. So that is why the sum of all of these, lambda 1 plus 2 lambda 2 plus 3 lambda 3 and so on up to L max times lambda L max, this is going to be the total number of edges. So that's an important thing to note. So if you take lambda prime of 1, this is always going to be equal to prime of 1. So this is by this I mean the derivative, and this is going to be equal to the number of edges. Okay, great. So this is some property of lambda prime and p prime. All right. So now we'll use another representation. So sometimes people like to work with this, but this implies that you know what n is. So we'll want to study classes of graphs for which we just let n to tend to infinity. So we want a notion of the degree distribution which is independent of the number of variable nodes or the number of checks. Only the rate has to be fixed. Okay, so that is why we look at what is called the normalized degree distribution. Which is simply L of x equal to lambda of x divided by lambda of 1, and R of x is basically equal to P of x divided by P of 1. So what is lambda of 1 equal to? It's equal to n, right? So what does L of x tell you, or what does each coefficient of L of x tell you? Correct. So it's basically each term gives you the fraction of variable nodes. So the coefficient of x power I is going to be the fraction of variable nodes with degree I. So in lambda of x, the coefficient of x power I was the number of nodes, whereas now you have the fraction of nodes with particular degree. Okay, so this is also sometimes called the normalized degree distribution from a vertex perspective, or just the normalized degree distribution. Will also sometimes be introduced in the following quantity, which is the normalized distribution, degree distribution from an edge perspective. Okay, so we'll call this again for the variable nodes going to be lambda of x. So this is summation I equal to 1 to L max lambda I x raised to the I, which is basically just going to be lambda prime of x, or in other words L of x going to be lambda prime of x, that is the derivative of lambda divided by the derivative of lambda evaluated at x equal to 1. The variable node for the check nodes, this is going to be called rho of x summation I equal to 1 to R max rho I x raised to the I, and this is p prime of x divided by prime of 1. But what does this basically represent? This basically represents the fraction of edges which connect to a variable node of degree I. Right? Because what is lambda I going to be equal to in terms of capital lambda, in terms of capital lambda I, let us. Correct. But can you get an expression for small lambda I in terms of the capital lambda I? Remember, it's a derivative of lambda of x, the coefficient of x raised to, sorry, I minus 1. So can you write down lambda prime of x? Huh? Times, right? Divided by lambda prime. Right? So small lambda I is basically equal to I times lambda I divided by lambda prime of 1. Correct? But we know that lambda prime of 1 is the total number of edges. I times lambda I is the total number of edges which connect two variable nodes of degree I. The ratio of this is going to give you the fraction of edges that connect two variable nodes. Okay. So why am I going about all of this? Why are we introducing all of this? Because we're not going to specify an entire ensemble just using these degree distributions. So we'll specify the degree distribution and we'll want to construct codes with this particular degree distribution. So you generate a random LDPC code with this particular degree distribution. So again, how do we do this? So let us say that let's pick a particular so let us pick a particular lambda of x and maybe so r of x, right? Sorry, p of x. So let's say that lambda of x equal to, what did we have earlier? So 3x plus 2x square and the p of x is 2x square plus x cube. Our goal is to construct a random LDPC code with this particular degree distribution. So how would we do this? What is the total number of variable nodes? Variable nodes, 5. Right? So I'll construct 5 variable nodes. Okay. Total number of check nodes, now really it doesn't matter how you order the variable. So let's maybe choose the variable nodes in increasing order of degree. So how many variable nodes do we have of degree 1? Have 3. So we need three variable nodes with degree 1. So I'll put one socket for each of these. And we have 2 variable nodes of degree 2. So I'll put 2 sockets for each of these. Similarly, I'll put sockets for each of these check nodes. So I have 2 check nodes, degree 2. So I'll put 2 sockets here, here. And I have 1 check node of degree 3. So I'll put 3 sockets for this particular. Right? Now I have a label for a number for each of these sockets. 1, 2, 3, 4, 5, 6, 7. And similarly 1, 2, 3, 4, 5, 6, 7. Now all I need is a random permutation. 2, and let me just pick some random permutation. 1, 2, 3, 4, 5. This is one random permutation. So 1 should go to 7. Means that this should go here. 2 should go to 2. 2 goes to 2. 3 should go to 6. So 3 goes to 6. 4 should go to 1. 1. 5 goes to 3. 5 goes to 3. 6 goes to 4. 6 goes to 4. And 7 goes to 4. So effectively, the LDPC code or the Tanner graph, right, is going to look here. So this would be one graph. You just picked at random. Correct? So that's the general approach. So you take any particular degree distribution, lambda of x and p of x. Let's say I have x squared plus 4x squared plus x cube, and maybe x plus x to the 5. So remember that these two can't be arbitrary polynomials. Right? The only thing that these two polynomials need to agree on is the total number of edges. Right? Because that, of course, the number of edges incident on variable node should be exactly equal to the number of edges incident on check. So we have to ensure that lambda prime of 1 is equal to p prime of 1. But otherwise, they can be arbitrarily chosen. So right now, I've just chosen something. So what is the total number of okay, maybe this is not thing. We change this to 4x plus x cube. What is the total number of edges equal to? 7. Right? The same holds even if I look at it from p of x. So how many variable nodes do I have? How many check nodes? 3. And I need sort of 7 sockets. First variable node has degree 1, second, third, and fourth all have degree 1. Third variable node has degree 3. Sorry, the fifth variable node has degree 3. Now same for the check nodes. I have 2 check nodes with degree 1 and 1 check node with degree 5. So I take a random permutation of 1, 2. Yeah, so if I want to construct a random LDPC code from the configuration model, then this is how I would do it. There are of course multiple codes, right? Now, of course, this approach doesn't necessarily give you a code with exactly this degree distribution. Okay, so let's see. So for example, if I took the following LDPC code, see, see, so for this, what is lambda of x? So it's the same as what we x this one. What is this? This is 4x plus x cubed. What about p of x? So it is the same as what we had over here. Now suppose that I picked one at random according to the model that I had just specified. What do? I take 1, 2, 3, 4, 5, 6, 7. I pick a random permutation. Okay, maybe the random permutation that I get, I run some random number, use some random number generator to do this. Maybe I get the following: 1, 3, 4, 8, 7. One permutation. Now let me try to construct the code. So 1 goes to 6, 2 goes to 4, 3 goes to 4 goes to 3, 5 goes to 6, 7 goes. So this gives me the following code or the following factor graph. So what is the actual degree distribution of this code? All of these have this. So what is lambda of x equal to? It's equal to 5x. X, and what is p of x? To x plus x cubed. Right? So in fact, just because we draw a random graph from this particular degree distribution, it doesn't mean that every graph that we draw is always going to have the same degree distribution. It could be different. That's a point that I'm trying to make over here. Right? And that is because some of these could be parallel edges. Right? Because in this particular configuration, it turned out that many of the edges were going between the same pair of variable nodes. Sorry, the same pair of variable check nodes. Right? And that's potentially a problem. But as it turns out, if you pick any degree distribution and you take n to be sufficiently large, then with very, very high probability, it's going to have the resulting graph, random graph, is going to have the same degree distribution with very high probability. The probability that there'll be sort of self loops or parallel edges is going to be very, very small. N is very large, then probability that there's a self loop here, the probability that there are parallel edges tends to 0 and tends to, which is enough for most of our purposes. In fact, one can prove some other properties as well. So if you look at the length of the shortest cycle, right? It turns out that if you let n tend to infinity, you fix a degree distribution. Okay, that's a constant. So L max is fixed, R max is fixed. You fix, let's say, small lambda of x and rho of x. Then for a given lambda of x and rho of x, it turns out that the probability that the smallest cycle is much smaller than log n. This is very small, very close to 0 for n sufficiently large. And this will particularly be important for us when we analyze the iterative decoding algorithm. So a very important property that we will require for belief propagation to work is that it should not have very short cycles. The larger cycles you have, the nice thing is that it looks more like a tree. Right? And we know that if it is a tree, then by the generalized distributive law, if we run the belief propagation algorithm, we are going to get almost MLD code. And that is what we're aiming for. And if you don't have very short cycles, then GDL will perform almost like the belief propagation algorithm will perform almost like M. But there's also another property that we should keep in mind. Remember that we are picking a random graph, or in other words, we're picking a random parity check matrix. Now, what can happen is that the parity check matrix need not be full rank. Right? The degree distribution could still be the same, but there's no guarantee that the parity that all the rows of the parity check matrix are going to be linearly independent. In fact, some of them could be linearly dependent. But as n tends to infinity, using this particular model, remember this is one particular model, right? You put the sockets and then you take random permutation and connect the edges. So this particular construction has a nice property that as n tends to infinity, the rate will be almost equal to so-called design rate. The design rate is what you want to aim for. But in general, some of the parity check equations could be linearly dependent. And if they're linearly dependent, then it means that the rate can only be higher. Not capacity, right? Forget about what the channel is. So you fix the degree distributions, right? You fix n, you fix m. So remember that n is equal to lambda of 1 and m is equal to p of 1. So if I give you lambda and p, or even let's say I give you lambda, I give you L of x and I give you say R of x and I give you n. So given an n, L of x and R of x, we can get lambda of 1 to be equal to L of x times n, and similarly you can get R of x as by computing the number of edges and then finding out what m should be. Right? So for a given n and m, you get the corresponding, you generate a random factor graph and you compute the parity check matrix H, which that factor graph corresponds. Now this could have, in general, could have linearly dependent rows. So the design rate is m by n. Sorry. The design rate is going to be n minus m by n. Right? So in general, m should be equal to n minus k. The design rate is going to be k by n. H is going to be an M by N matrix, right? So this is what we want to get, what we have designed for. But if the rows of the parity check matrix are not linearly independent, then fine, the rank is not equal to M. It should be something less than M, and therefore the actual rate is going to be higher than N minus M by N. So in general, the actual rate is going to be greater than or equal to the design rate. But as it turns out, under some conditions, on the degree distributions, lambda and rho, you can show that if you pick a graph at random, then the probability that the actual rate, so let me call this R of T, is greater than R of, let's say, dV lambda rho plus nu is sufficiently small. Okay, in particular, if it's a dV/dC regular LDPC code, then dV/dC, this is the design rate. So this is either equal to the design rate with high probability, or it's equal to the design rate plus 1 with high probability. That is something that you can show. Okay. So just a quick recap. So now we've seen for a given LDPC code, if you want to use this for a binary input channel, then we have we have a mechanism, we have an algorithm to decode this, the belief propagation algorithm. And we also have a simplified message passing rule for this. Okay. And now we know, given a particular degree distribution, we know how to construct a random LDPC. Okay. And at least when we do some simulations, it turns out that if you pick a code at random and then try to decode this, it performs really well. Take any general binary input symmetric channel, say the BEC or the BSC, you get the probability of error turns out to be very, very small. But the question is, how do we really characterize this? So you can't just choose lambda and rho arbitrarily. Some lambdas and rhos get you all the way up to capacity, whereas some of them fall short of achieving capacity. So how do we design this? How do we actually analyze this? It's not entirely easy. So now, instead of studying individual codes, as I mentioned, you can study ensembles of codes. So instead of designing the entire code, instead of designing the entire H, our problem now has boiled down to the problem of designing just lambda and rho. If we know how to, and these are constants, right? So you don't have too many parameters. It doesn't grow with block length. So, but even then, so the space is now much smaller. Let's say maximum degree should be, say, 15. So you have a total of 30 variables, but your block length could be like 1 million. But now, how do we optimize over this? How do we, what exactly is the objective function? Because we don't know how lambda and rho actually connect to the error probability. And that's the goal. And we'll see in next few classes, we'll make some assumptions. In particular, we'll use some of these properties to make certain assumptions. First assumption will be that it suffices to just study the probability of error when you assume that all zeros code word is transparent. it turns out that no matter which code word is transmitted, the conditional probability of error is always going to be the same. The second assumption we will make is that is this particular condition. So we know that with high probability, you're not going to have small cycles. So, and if you run the belief propagation algorithm for a certain number of iterations, you can make this assumption that the graph is almost behaves like a tree. And that, in fact, will turn out to be the most crucial assumption and the most crucial property that we will use to study or analyze the probability of error. Okay? So let's stop here. Any questions?